Hi everyone, Kamran Nouri here. In this video we talk about rotational inertia and rotational kinetic energy. Previously we talked about rotational kinematics and angular velocity omega as an object rotates about an axis, which is the rate of change of angular position theta in radians per second, and angular acceleration alpha as the rate of change of omega in radians per second per second. We also talked about the relation between the angular and linear speeds. When a solid object rotates at an angular speed omega about an axis, each one of its points circles the axis of rotation with a linear speed v that is proportional to the radius of its circle or the distance of the point to the axis of rotation. So v equals r times omega. Now we will see where the formulas for rotational kinetic energy or rotational inertia come from. Theta is s over r, omega is d theta over dt, alpha is d omega over dt, s is r theta from here. If you take derivative, you get v equal to r omega. Means if something is going around with angular speed omega at distance r from the center, it is moving at speed v, tangent to the circle. And it has also tangential acceleration. And we also have, because that thing is moving on a circle, it has also radial or centripetal acceleration. We call it AR, or sometimes they call it AC for centripetal or radial, which is v squared over r. And because v is r omega, you can write r squared, omega squared. One of the r's cancel, you get r omega squared. So r is also r omega squared, if you need. I want to now try to find out, if we have an object that's rotating, what is its kinetic energy? Because rotation is motion. You want to find the kinetic energy of rotation. So let's say we have an object that is made up of several point masses. Each one has m1, m2, m3, in general mi. And then it is rotating around an axis. Let's say this is the axis of rotation. Axis of rotation perpendicular to this page by passing through this point, right? And this is a solid object, means the distance between the masses don't change, right?
How do we know that it's coming towards us?
It's what I'm assuming.
Okay.
The axis is this axis, means this object is rotating like this, right? I want to see that, what happens in the rotation, right? So the axis is like this, out of the page, and it's rotating in this plane, which is perpendicular to the axis of rotation. So, as I said, this object has a total mass m, which is sum of all these particle masses. It is a solid object, means that the distance between the particles doesn't change. So it's all moving as one part, like this. When this is moving, the distance between here and here doesn't change, right, in motion. If the axis is here, it's moving, and everything moves together as one object. So, in general, it has a general shape, and this is the axis of rotation. And each particle is moving because of the rotation. And it's rotating at angular speed omega. Right? The whole thing is moving at angular speed. This particle is closer. It's moving perpendicular to the radial distance. It's like this. Right? And its speed is r times omega. If the r is small, the speed is small, right? If r is large, the speed is larger, right? So if that one moves with this speed, v1, this mi has this radial distance ri, and moving perpendicular to that, and it's moving faster because it's farther away. Everything has the same omega. The farther it is, the faster it goes, right? So this is vi. This mi moves at the speed vi, and v is r times omega. vi is ri omega. So if I want to find all the kinetic energies, kinetic energy of the first one is 1/2 m1 times v1 squared. kinetic energy of the second one is 1/2 m2 times v2 squared, and so forth. If I add all of them, I say the total kinetic energy for rotation is equal to sum over I and 1/2 mi vi squared. So we add all the kinetic energies together like that, and then according to this, because all of them are moving around this axis at angular speed omega, then v for each one is r of that times omega, right? So for vi, I can write ri times omega. K rotation is equal to sum over I, 1/2 mi ri omega squared, right? And then we get ri squared omega squared. Right? And then this 1/2 is common in all terms. Omega is common in all terms. I want to factor 1/2 and omega. So K for rotation is equal to 1/2 the sum of all mi ri squared times omega squared. Right? This is called rotational inertia. We introduce I, which is sum of mi ri squared, and we call it rotational inertia or rotational mass. Why do we call it like that? Because now we can say K for rotation equal to 1/2 I omega squared. But remember, K for translation is equal to 1/2 m v squared. Instead of v, we have omega. Instead of mass, we have I. This I acts like a rotational mass. It is the central quantity in this part of the course. It's very, very important. Sum of mi ri squared. That acts like a rotational mass. That is not only depending on mass, but also how mass is distributed around the axis. Remember over there I told you that how the mass is distributed around the axis. If you have a cylinder or a ring or a sphere, this is where it comes from. And this I is very important. So, now what is this I for different cases? For example, if you have a simple stick like this, is rotating around one end or around its center. How do we find it? We don't have individual particles, so we cannot do this summation. But what do? We can take small pieces and take that as a particle, and then add all the pieces together around whichever axis you want. For example, if you want around the axis rotation here, this one value. Around the axis rotation here is another value. Around the axis rotation at the center is another value. So that not only depends on the mass, but also depends on how mass is distributed around. For example, around this axis, some of the masses are far away. But if you take an axis here, on average, the masses are closer to this axis, right? So you expect less rotational inertia around this axis than around this axis, right? So let's see how it works. Let's try as an example to find the rotational inertia for a thin rod of length L. If I have a thin rod like this from here to here, let's say it has a length L and it has a mass M, and I want to find rotational inertia around an axis that goes through the one end of it and is perpendicular to the rod itself. In fact, the axis of rotation is Z, right? Which is passing through the end, and it is perpendicular to the rod. Does it make sense? How do I do that? If I had this number of particles, I would use this I equal to sum of mi times ri squared. But I don't have individual particles. So what I do is to divide it into small pieces, so each piece is small enough so that it acts like a particle, right? So this has the mass dm and also length dx. And instead of this formula, I can write I equal to integral, because summation is like integral, r squared dm is the mass times the distance to the axis squared. And the axis is z-axis. What is the distance of this to z-axis? That on the x direction is called x, right? So for this, I can write I as integral of x squared dm. But dm doesn't make sense. I want to integrate over x. So I have to write dm in terms of x or dx. How do I write dm in terms of dx? Yes?
I think you do dm over dx equals to m over l.
That's right, exactly. Dm, because it's mass of the length dx, is equal to the total mass m over total length l. So then dm will be m over l times dx. So therefore, dm is m over l times dx. You see, I'm just following the math. The mass is uniformly distributed. So we have this, and then you put that in here, then you have x squared dx. Right? So let's see, I becomes integral of x squared m over l dx. And m and l are constant. I can take them outside. And integrate over x. What are the limits of integral? I should go over the masses, right? What is the limit?
0 to l.
0 to L, very good, yes. So I put the m and L outside, m over L, integral x squared dx, from 0 to L. M over L, what is the integral of x squared?
X cubed over 3.
X cubed over 3, evaluated at x from 0 to L. So if I put 0, I get 0, but if I put L, I get what? M over L, L cubed divided by 3, right? So I becomes M over L, L cubed divided by 3, but one of the L's cancel. And then you can write this as I equal to 1/3 M L squared. And this is for the formula that you find in your book. It says the rotational inertia for a thin rod rotating around one end axis of rotation that's perpendicular to the rod. Has mass m, length L, so this is the formula. For example, if you want to find the rotational inertia of this around this axis that's rotating right now, you multiply the mass times length squared divided by 3. Alright? But what if it is rotating around the center? Like if this is 1 meter around 50 centimeters like this, is it the same? No, you don't expect it to be the same, right? How do you do that? Then you can set an axis here, right? Then let's do that quickly. If this is your rod, and you put x-axis this way, and y-axis this way, and z-axis perpendicular to that, and now it's rotating around z-axis, you do the same thing, dx, everything will be the same thing, right? The integral of x squared dm, and dm will be the same thing, and then you put that in here, you get everything the same. I becomes m over L x squared dx, but the limit of integral changes. What is the limit of integral in this case?
0 to L over 2. Or negative L over 2 to L over 2.
Negative L over 2 to L over 2. So I will be the same as this integral, m over L, integral x squared dx, from negative L over 2 to L over 2. And then, because this is an even function, over a symmetrical interval, you can write twice from 0 to L over 2. Right? You remember? If you have an integral of an even function from negative a to a, you can write twice from 0 to a. right? So you can say this is equal to 2m over L, integral from 0 to L over 2, x squared dx, and then you get 2m over L, x cubed divided by 3, and evaluate between 0 and L over 2, right? So what would that be? For 0 you get 0. For L over 2 you get L cubed divided by 2 cubed. But one of the 2 cancel with 8 becomes 1 over 4 times 3. So it becomes 1 over 12 m L squared. But one of the L's cancel also, right? So you see, around the center of the rod, if the axis of rotation is perpendicular to the rod, but passes through the center, the rotational inertia is 1/12 ml squared. Right? I hope you enjoyed this video and thanks for watching.